Dear students, in this class 6, we learn one beautiful idea. Just observe what I write, and then we proceed on to other things. Say, I take air and water again. Say, this is the surface of separation. We imagine here air is there and here water is there. Now we imagine a light source, yes, at this point inside the water. I write a ray of light coming from the light source straight along the normal to the interface like this. This is the light ray which passes without any deviation as angle of incidence is 0 here. Now, if I draw another light ray from the sources which is near to the normal, I have to write down like this. Just observe. This is, and I write the normal also here. I write the normal like this. Now, as you know, this light ray is moving from denser to rarer, water to air. It should bend away from the normal. Therefore, angle of refraction is larger than angle of incidence. And this will be our refracted ray. Now, this is angle of incidence. I1 I call. Now, I write another light ray from the same source, but at slightly larger angle than I1, like this. Now, if we draw the normal again, just observe what will happen to the angle of refraction now. As angle of incidence is increased, angle of refraction must also increase. Therefore, the refracted ray for this angle of incidence will be having more angle of refraction. Say, I write it like this. Just observe, this is our R2, the angle of refraction, and this is our R1, angle of refraction for the first case. Just observe, when I1 is smaller, angle of refraction is smaller, but larger than I1. When I2 increased, angle of refraction also increased. Now it comes to our mind, there may be a situation like this. Let me extend this figure like this. There may be a situation like this where a ray of light from the same source is incident at a suitable angle like this. If we draw the normal where the say like this, the refracted ray will pass on the surface of separation like this. This is a special case in the refraction. Say it passes on the surface, it grazes on the surface. Here, the angle of incidence is what we call specifically IC, or many times denoted by C only. Observe the angle of refraction, R3, will be 90 degree here. That means whenever a ray of light travels from denser to rarer, there is a particular angle of incidence, what we call as IC or C, for which angle of refraction becomes 90 degree. That means This angle is very special as angle of refraction is 90 degree. And this angle denoted by ICRC is called as critical angle. Critical angle. So, what is critical angle? It is defined as angle of incidence for which angle of refraction is 90 degree when ray of light moves from denser to rarer. So, critical angle, once again, is the angle of incidence for which angle of refraction is 90 degree when light moves from denser to rarer. Observe, it is not required to say denser to rarer. Why? Because this case, the angle of refraction becoming 90 is possible only when the light moves from denser to rarer, as angle of refraction is larger than angle of incidence. This is not possible when light moves from rarer to denser, because in that case angle of refraction is always smaller than the angle of incidence. For no angle of incidence, angle of refraction cannot be 90 degree. Therefore, this situation is possible only for the light ray to move from denser to rarer. At this point, can we write an expression for critical angle? We go for that. Before that, let me repeat the definition for critical angle once again. Critical angle is the angle of incidence for which the angle of refraction is 90 degree when the ray of light moves from denser to rarer medium. Now, we start deriving expression for critical angle assuming the first medium refractive index as N1, second medium refractive index as N2, and applying the Snell's law. For that, we can write a simple figure once again. Say I take this as the surface of separation and this is the normal, and let me write an incident beam at critical angle. We write the normal once again. Now we write the refracted ray which grazes over the surface. Say this word grazes is very important because in many numericals grazes word is used for all those things. You must take angle as 90 degree with the normal. Now we write this angle as C and this as 90 degree, and this is of medium of refractive index N1, this is of medium of refractive index N2. This is the first medium and this is the second medium. Now applying Snell's law, I can write Snell's law in the form N1 sin I equals N2 sin R. We can write now N1 sin C equals N2 sin 90 degree. N1 sin C equals N2 as sin 90 is 1. As sin 90 degree is 1. Therefore, we can simply write sin C as N2 by N1 for air as second medium For air as second medium, N2 will be 1 and I call N1 as N, then sin C equals 1 by N or N equals 1 by sin C. From the point of view of examination, it's an important derivation. You may be asked to prove N equals 1 by sin C. Say we just go through it once again. Let us think of like this. Say here I have written this ray, say as incident ray, what I can call as OP, and PQ is the refracted ray. 90 degrees is the angle of refraction R, C angle of incidence I. Then by applying this Snell's law from in the form N1 sin I equals N2 sin R, N1 is N1, I is C, so N1 sin C, N2 sin R is 90, or N1 sin C equals N2, sin 90 is 1, sin C is N2 by N1 for air as second medium. Now, N2 is 1, N1 is infinity, N1 is N, yes, sin C is 1 by N, N equals 1 by sin C. This is an important derivation. Now, can you imagine what happens if the angle of incidence becomes more than critical angle? We try to write down the figure and then we come across a new concept which is very helpful in modern days in medicinal diagnostic tools or in our internet capacities. All these things are governed by the phenomena what we are going to learn now. Say this is the surface of separation. I write a normal here like this, and also I extend this surface of separation between the two media much more. Now we imagine light rays from the source start traveling at an angle of incidence equal to critical angle like this. Say we write the figure what we already learnt. Can you tell me what is the angle of refraction now if the angle of incidence is critical angle? As you guessed, it is right, it is at 90 degree. It is at 90 degree like this if this angle is critical angle. If another ray of light which is incidenting on the surface of separation with slightly more angle than critical angle, what will happen to this light ray? I am writing it in green color. Just observe. What will happen to this light ray? What is the angle of refraction for this situation? Can you guess? Say, as we said in the discussion of critical angle, as the angle of incidence increased, angle of refraction also increases till 90 degree. After the angle of incidence I becoming greater than critical angle, can you guess what is happening? Say angle of refraction should be more than 90 degree. That means the ray will be in the first medium only. That means the ray gets reflected back into the first medium. That is, when angle of incidence is more than critical angle, the ray will not undergo refraction. It comes out or it gets reflected back into the same medium. This phenomena is what we call as total internal reflection. Total internal reflection. Why it is total? Why it is internal? We want to learn now. Say, whenever a ray of light, whenever an electromagnetic wave, whenever a radiation fall on any medium, three things happen. One is reflection. A part of that is refracted, that is transmitted. Remaining part get absorbed. Three things: reflection, transmission, absorption. But observe, to make this figure proper, I have to add a reflected part on the for the angle of incidence I equals C. But for the I equals more than C, all the light gets reflected, there is no refracted light. That's why we call it as total, because all the light gets reflected. Why it is internal? Because it is inside the first medium itself. That is why it is internal. Now, we try to define total internal reflection. It is the phenomenon in which a ray of light gets reflected back instead of being refracted when angle of incidence is more than critical angle and light moves from denser to rarer. The another way and the easiest way is total internal reflection is the phenomenon in which a ray of light moving from denser to rarer gets reflected when angle of incidence is greater than critical angle. This is the definition for total internal reflection. Can you guess the conditions for total internal reflection? First is very simple as you guess. The total internal reflection is possible only when light moves from denser to rarer. As we said in case of critical angle also. Critical angle possible only when light moves from denser to rarer. Because of the same idea, total internal reflection is possible when ray of light moves from denser to rarer. That is, first condition is to move from denser to rarer. Can you guess the second condition? It is in this figure. The angle of incidence should be greater than critical angle. The angle of incidence must be greater than critical angle. These are the two conditions. Say, we just go through it once again. The two important conditions for total internal reflections to happen is, one, ray of light should move from denser to rarer, and angle of incidence should be more than critical angle. This total internal reflection causes beautiful natural phenomena. At the same time, this helps us in creating many technical applications. For example, few years back, say if somebody goes to a doctor with some problem in esophagus, that doctor used to take the X-ray of esophagus by asking the patient to drink barium oxide, and as the flesh is not obstructing the X-ray, doctor asked patient to drink the barium oxide, which gets coated inside the esophagus, and once the barium is coated, say the doctor can get the X-ray and see into the problems inside the esophagus. But nowadays that is not the case. Doctors ask patient to swallow a pipe, and then through that pipe doctor can see any abnormalities inside the esophagus. That is possible, that is made possible by this phenomena, total internal reflection. Nowadays, you are getting much faster internet connections through what is called as FTTH, that is fiber optic technology. In fact, that fiber optics is also made possible by this total internal reflection phenomena. Therefore, nowadays this total internal reflection phenomena is very important for our day-to-day life as we are more dependent on internet nowadays.